Okay, good afternoon, everyone. We get started today. Before I forget, there won't be any lecture this Friday because this is a wellness day at Harvard. So I won't have a lecture or a discussion session. But we'll have a discussion session tonight at 9 p.m. As on previous days. So there was also, I encourage you to add questions on Slack. There was a brief discussion on Slack about just the meaning of the factorization. And let me just comment on that a little bit before I start my lecture. Hello? Someone have some other question or comment? I mean, please go ahead anyway. Okay, so let me just comment on that question. So the question that when you have a Hamiltonian like this, with this term over here, then this factorizes when you take a Slater determinant ground state into these two terms. And I just want to state that that statement is completely equivalent to a statement we made earlier in the first quantized normal theory. So in the first quantized theory, we took some two-body interaction V, and then we took a Slater determinant wave function where we occupied some set of states phi alpha. And then I asserted, without going through the details of the determinant calculation, if you want to see the details, I've put some notes up under the notes folder where somebody has explicitly gone through a few more steps than I have written out here. So when you take the expectation value of this V, you get two terms. There's what I call the direct term and the exchange term. And these two terms here are in one-to-one correspondence once you write out everything in the basis to these two terms over here. So that this is the direct term and this is the exchange term. It's really the same thing in just a different language. So one way to prove this is to actually prove it in the Hartree-Fock language, which you can see in the notes, or you can just do everything in the second quantized language. And then to prove it, you would do something like this. You would say, well, first imagine that your ground state, psi, is product on alpha on some C dagger alpha times the vacuum. Okay, and then you have these operators, C, D, E, F. So say the last one of them, F. What you're going to do is, since these you have a complete set of states, phi alpha, you can also expand F in terms of the C alpha. So there's some expansion of F with some coefficients here. Let me just call them F sub alpha, and these are operators. So these are operators and these are numbers. So there's some coefficients. Now, since this expression is linear in F, linear in any one of the operators, if it holds for the basis set C alpha, it also holds for any linear combination. So it's really sufficient to take the simplest case where every one of these operators, C dagger F, C, D, E, F, C, are just some of the C alphas. So basically, all you have to do is take some of the C alphas, C dagger alpha, C dagger beta, C gamma, C delta, and evaluate this expectation value, where psi is given by this. And that you can do by just using the commutation relations and using the basic defining relation that the vacuum is annihilated by 0 for all alpha. So once you know this, and you know the commutation and anti-commutation relations, and you can plug this in here, you just work through all the commutation relations and you can prove it. Just by, basically the idea is when you write this out, what you want to do, if you write this out more explicitly, what you have is C dagger alpha, C dagger beta, C gamma, C delta, and then you have product, and let me call this epsilon, because of the dummy index, C dagger epsilon acting on 0. And on this side, you have product on alpha, beta, gamma, delta, epsilon, mu, C mu acting on 0. And the conjugate of this, of course, is that 0 C dagger alpha is also equal to 0. So basically, the trick is that you keep moving the C dagger through these until you hit 0 and you get a 0. And you keep moving the daggers this way until you get a 0. And what you find, if you just look at the combinatorics of that, is you get the answer that I wrote down earlier. Okay, so that's how you prove this. In fact, yeah, all right. So I'll just leave it at that. And if you want more discussion, we can discuss tonight in the discussion session. All right. So last time we did a theory of the electron gas, and we, in particular, the properties of electrons moving at uniform positive background. And all we did was just apply the Hartree-Fock factorization and on this Hamiltonian. So one choice for the Hartree-Fock factorization was a translationally invariant state, and that pretty much demanded that the electrons be in plane waves. And once you have that, then we got some energy, which we wrote down as a function of this RS, get some number here. But another choice is to imagine that the electrons form a crystal. So at least at 0th order, then these are still a Hartree-Fock wave function, except that the electrons are localized now in these states at delta functions at some positions Ri. And you optimize those positions to optimize the potential energy. And in 2 dimensions, we found that worked best for the triangular or hexagonal lattice. And then there are corrections to this energy from phonons and ring exchange, and then it becomes a very complicated situation where you go from a gallium liquid, a metallic state at small values of Rs to, in this case, an anti-ferromagnetic crystal, and then finally a ferromagnetic crystal. And this is only known through Monte Carlo results. All right, so that's kind of where we stopped. Are there any questions on anything we've covered in the course so far? Okay, then let's start the next chapter, which is ferromagnetism. So ferromagnetism, is a basic phenomenon involving symmetry breaking, where in the simplest case, you have some spins in a material and they choose to all point up or all point down as you lower the temperature. In fact, that does happen in some metals like iron or nickel, that as you lower the temperature, they become ferromagnetic. And we want to do a very simple theory of that in called the Stoner model, which captures the basic physics, although it's not quantitatively that accurate. But before I even come to the Stoner model, I want to spend a little bit of time talking about the basic characteristic of ferromagnetism, which is the one of symmetry breaking. That is, the upspins and the downspins have essentially exactly the same energy, and the system below a certain temperature decides to choose a preferred orientation. Okay. And the fact that this happens and the very simple theory of this really goes back, is developed in the context of a much simpler model, which I'll just describe, which is the Ising model. And the basic ideas here, in fact, go back, I think, probably to van der Waals and the van der Waals theory of the liquid gas critical point. And the context of magnetism is sometimes called the Curie-Weiss theory. And general frameworks for this in all kinds of contexts is sometimes called Landau theory. So, all right, so let's just take the very simplest models, which you have symmetry breaking. So it's just a model of binary variables sitting on some lattice. Sigma I can be plus or minus 1. And then there's a coupling between the sigma I so that they lower their energy if they both have the same orientation. So if these are both plus or both minus, then you have an energy minus J. And if they have opposite orientation, you have an energy plus J. And you just do the stat mech of sum over all sigma I of this very simple model. So this is called the Ising model. It's exactly solvable in one dimension. And Ising solved it in one dimension and found that it wasn't ferromagnetic and was disappointed. But that turned out to be an artifact of one dimension. Later on, Sagar solved it in two dimensions, and so showed that it does indeed have a broken symmetry phase. And it's not solvable in three dimensions, and understanding the structure of the Ising model in three dimensions has led to, in fact, it is what led to the development of the renormalization group and all this very fancy field theory that we won't cover in this course. But here we just want to apply the simplest mean field theory, which formally becomes exact to the limit of infinite dimensions. But it does predict the existence of a phase transition, which we now know exists above 2 dimensions at finite temperature. Okay, so one way to think about the mean field theory is very much like what we did in Hartree-Fock, is you just replace this term here by where you replace some of the spins by their average values. You take sigma I, sigma j on every bond and replace it by average of sigma I times sigma j plus sigma I times the average of sigma j. And then because there's two terms where you originally had only one term, you subtract twice the average value, just a constant, to correct the overall energy. That's really all there is to it. So it's the basic factorization. Now you can just pull it out of a hat and say, this is what I'm doing. And that's pretty much what we're going to do. But just as with the Hartree-Fock theory, for this model at finite temperature, so the Hartree-Fock theory was a 0 temperature for a quantum system. This is for a classical system at finite temperature. You can justify this by a variational principle, which I'm not going to cover. There's a few pages of notes on the website that describes the variational approach. Okay. But let's just go ahead and do this and see what you get. All right, so it becomes extremely simple. So you just take this term and just plug it in here for every bond. Okay, so I'm going to write it this way. So all I'm doing is inserting this in here. The main assumptions I'm going to make is that this average value of sigma, this average value of sigma I on any site is independent of I. That may not be the case in some systems, but for the case where J is positive, where it's ferromagnetic, that is correct. So we just assume sigma I is independent of I, and that independent number I'm going to call M. Okay, so there's an unknown number M, which is just the average of sigma I on any site. So I just now take this factorization and just insert it in here and collect the terms, and what you find is you can write everything in the following way. There's an overall constant where n is the number of sites, m is the magnetization, z is what's called the coordination number, or the number of neighbors of each site I. So this symbol means sum over nearest neighbors. So you get some constant which actually comes from this term. And then you have some field, which I call a field, hi, which is acting on sigma I. So hi is a number, and its number is related to m, it's jzm. Okay. So if I just look at this now, the nice thing about this term, in contrast to this term, is that the different spins are independent. The Hamiltonian is just the sum of terms where the first term depends on spin 1, the second term depends on spin 2, and so on. So when I put it up in the exponential, those terms factorize. And this very complicated sum, I can now just do on each factor separately. So the whole thing just factorizes. So the partition function, becomes something like, apart from an overall constant, the partition function z is just proportional to product on G on Z sub J, where Z sub J is a partition function on side J. And what is the partition function on side J? Well, it's just this field. It's just this term for side J. So it's sigma J equals plus minus 1 of X, this thing, where M is the average value, and I may as well take the average value on sigma J. So this is like the loop equation. This is the partition function which depends on M, and then the value of M depends on the average of sigma in the partition function. So you have to solve this self-consistently. So first of all, Zj is easy to evaluate. It's just cosh of 2 cosh of JZM over T. And what is the average value of sigma J? Well, you just have to put a sigma J here with the probability and the rules of StackMech. And that gives you a cinch. So M then is the ratio of this to the partition function, and you get a tanh. So this is the basic equations of the Ising model, the mean field equation or the Curie-Weiss equation. That M is tanh of M with this constant. So this is a nonlinear equation for M that you have to solve. And once you solve this, then okay, you're done. Well, not quite, but at least you have some guess at the solution. So the way you do this is you solve this graphically. So you plot the left and the right-hand side of this equation as a function of M. Then at very high temperature, what you find is that, so here's M, the left-hand side, and here's the tanh, the red line. And at very high temperature, it's very flat. And so there's only one solution at M equals 0. But if you lower the temperature, the tanh becomes much sharper, like this line here. And now you notice there are 3 solutions, 0, minus M, 0, and minus and M0. And those are the solution of the Curie-Weiss mean field equations. Okay, so which one should you pick? So there are 3 solutions. Well, it seems kind of natural that this solution or that solution are equivalent anyway. They're just overall flip of the spin. So you should pick, and that would be the symmetry breaking between picking this one and that one. You have to decide which one, it's random. You can pick either of them. They should have the same energy. But this one is a little more problematic. I don't know whether I should pick this one. Certainly above TC, above this temperature TC, and the value of TC, where you go from 1 to 3 solutions, is just exactly Zj. You can easy to work out from the structure of the tanh. But should you pick this or should you pick those 2? Well, okay. So you have to pick one or the other, you have to know the free energy. So we need the free energy. So we have to go back now and keep track of this overall constant here to get the free energy, and which is related to this overall constant there, which we've just dropped. So we have to keep track of this overall constant and get the free energy of those 3 states. Okay, so like I said, to really do it properly, you have to do a variational calculation, but we won't bother with that. So the free energy of the single spin of the on side J with just a field is just minus T times the log of Zj, which is, and Zj is 2 times cosh of this thing. And the total free energy, the sum of the free energy of all the spins, plus this correction, this overall term, which is just a constant and has an n, depends on the number of spins. And so you have to add that term. And so when the dust settles, this is the expression you get here. The mean field free energy at magnetization M divided by N, free energy per site, is some function of M, of the magnetization, minus T log this thing. And this free energy is actually a variational estimate, but there's a more complicated calculation to really prove that at finite temperature, which is in the notes that I put on the website. Okay, the first thing you notice, so you've got a free energy function of M. You can get the equation for M, the Curie-Weiss mean field equation, by just taking the derivative of M with respect to M. So we want a minimum of this free energy because it's a variational estimate. So dF dm better be 0. And if you apply that to this equation, you get the same equation as before. So you can kind of breathe a sigh of relief. That's a good check on this calculation. But now it allows you to tell us, now I have a number here, and I can look at what this number is between this point and that point, and pick the right solution. So the conventional way you do this is you plot this function fmf as a function of m. So this is fmf here. So if you plot it as a function of m, what you'll find is that for higher temperature, it looks almost like a parabola. It's not quite a parabola, but it's some function. I mean, this is the function. We're just plotting this function. Well, I have just sketched something random, of course, with my hand. Why isn't that erasing? Oh, there it goes. But for t less than tc, you go from a function that's shaped like this to the famous, well, it's sometimes called the inverted Mexican hat, for when you have two component order parameter, but this double well type potential. It has two minima at plus and minus m0. So obviously these are lower in energy than S. So there are three solutions of D where the derivative of F with respect to M vanishes here, here, and here. And obviously these are lower in energy. And you have to pick one of them, and that's in a nutshell is the theory of mean field theory of magnetism of Curie and Weiss. It's closely connected, as I said earlier, to the van der Waals theory of the classical gas, where also you minimize the free energy with pressure and volume as your parameters. And it's basically correct, and it becomes quantitatively correct even the higher the dimension of your system. Now, you can teach whole courses and write books about what happens when T becomes close to Tc. And what happens is this potential becomes flatter and flatter and flatter, and then eventually it turns down. And what's happening right there, well, that's a whole subject for field theory and RG and epsilon expansions and all kinds of fun stuff, which we will not cover in this course. All right, so the quick description then of StatMech, which of the Ising model and how it has a ferromagnetic solution in which these sigma I, which I think of spins of some electron, which can only point up or down. So there's no full spin rotation symmetry. So it's a very simple model. But if you had sufficient spin orbit coupling in some insulator, this would be a reasonable way to talk about ferromagnetism. But we are interested in metals like iron, which is not an insulator, and this is not really a reasonable approach for iron if you want to get any sort of numbers or connection to the microscopic physics. Okay. Any questions? All right, so let's go back to electrons. But the reason I went through that is because we're going to do this. What we're going to do is the logic of it is going to be exactly the same as far as the structure of the mean field theory goes. But the computation of the energies is going to be fully quantum and in a metal, not in an insulator, where we also worry about the fact that the electrons can move around in addition to worrying about their spin. Okay, so this analysis that I am going to now present, I could equally well carry out using the electron gas Hamiltonian. There's really nothing, if I'm doing mean field theory, nothing stops me from doing that. It's just that I will have messier equations. Everything will go through with many more sums and momenta sitting around all over the place. So I'm going to just simplify my life and consider another model, which is also, extremely widely studied in condensed matter physics. And it's kind of a cousin, of course, the electron gas Jellier model. And it's a model in which you take the long-range Coulomb interaction and you just replace it by an on-site interaction. So there's some interaction U where acts only on one site. And on that site, then if you have two electrons, necessarily they'll have to spin up, and each site can only have one orbital. So each site can only have one, there's only one orbital on each site. So that's what, I should, before I talk about this, I should very quickly remind you of what the tight binding model is. So here's the model we're talking about. That page. Okay, sorry. So we had previously in Gellium. Okay, let me just show that. Gellium. Our Hamiltonian was, let's first talk about the kinetic energy, was just h bar squared k squared over 2m c dagger k ck. So now we take a model on site. So on each site, there's only one orbital. This is called a tight binding model. This is real space. This is site, I plus 1, I plus 2, and so on. Could be in any dimension. I'm just showing you one dimension. And on each site, you have an electron, which can either have spin up or down. So there's an operator, Ci dagger sigma, which creates an electron on that site with spin sigma. Okay, so you could have an electron here with spin pointing in any direction, electron pointing in that direction. And then this electron can hop from site to site, and the so-called tight binding model. And the matrix element for this is, we're going to say, is minus T. So then the Hamiltonian, the kinetic part of the Hamiltonian, just becomes sum on I, or really sum on nearest neighbors, Ij, minus T C dagger I sigma Cj sigma plus summation conjugate. Actually, this is a problem in the homework. And when you take a Fourier transform, you can write this as sum on k epsilon k C dagger k sigma C k sigma, where epsilon k is minus 2t cosine kx plus cosine ky. And if you're in 3D, that'll be cosine kz and so on. Okay, so showing this is one of the homework problems. So this is the simplest tight binding model with one orbital per site. And so this replaces the kinetic term of Gellium. Now the kinetic term is this. Okay, and then Gellium had a Coulomb interaction, had a term like this plus sum on k prime q. Well, okay, becomes kind of complicated. That's why I'm not using it. But it was something like 4 pi e squared over q squared. And you had C dagger k plus q sigma. Let me see if I can remember this. C dagger k prime minus q sigma prime c k prime sigma prime c k sigma. Okay. So that was what in momentum space and has some complicated term in real space. And we're just going to approximate that. We're going to say that so this interaction has a very long range form in R. It has a 1 over R tail, and that led to some difficulties. It led to this log divergence we saw last time in the quasi-particle dispersion or quasi-particle effective mass. But as I asserted at that time, that if we're going to show in the next few weeks that long range part is actually totally fake, it undergoes the phenomenon of screening. So in any real metal, the long range interaction gets screened and gets cut off effectively by the fact that any free charges are screened by readjustments of the liquid. And so the long range interaction in the end, if you're not interested in screening per se on its own, can be just ignored. So we're going to focus on the short range part, and that's the concept of the Hubbard model. We assume that screening has somehow been taken care of, and we simplify our life by just ignoring it because it's just susceptible to screening anyway, and just only keep the short range part. So if I keep only the short range part, well, the shortest range part that you can't throw out is if you have two electrons on the same site. So you have two electrons, one here and one here, both on the same site. Well, they better have opposite spins because there's only one orbital. by the exclusion principle. And so I add a term which is only operative if you have both electrons present. So and the coefficient we call U, sum on I, Ni up, Ni down. And what is the value of U I should take? Well, one point of view, from the Jellium point of view, is just, you know, this sum on I is basically summing over all possible momenta, and the basic interaction depends on this difference of the momenta. So you have two particles with two different momenta, and if you had particles with two momenta in k and k prime, the interaction term is roughly k minus k prime squared. So you can say it's just the average value of this around the Fermi surface. So you take the integrals in k and k prime around the Fermi surface, or inside the Fermi surface, really, and you say U is equal to approximately this. So that would be your first guess as to what value of U you should put in. And if you actually go through the Hartree-Fock theory of magnetism in this theory, if you actually work out the Hartree-Fock theory of magnetism in this theory, which I think may well be done in the book, or I'm sure it's done in many other books. I think Donyak and Sondheimer certainly goes through it. But I'm pretty sure it's also in Bruce and Flensburg. So you could do Hartree-Fock theory with that, and when the dust settles, you get pretty much the theory I'm going to describe, except U will be replaced by something like this. All right. So that actually a good idea for a homework problem. Anyway, so that motivates the Hubbard model that we're now going to talk about. Okay, so that's the Hubbard model here. And we're going to see it over and over again because the Hubbard model, is also believed to be one of the key models in understanding high temperature superconductivity and all kinds of other correlation effects. All right, questions? Okay, so this is we just take this as a some model of ferromagnetism. It's an artificial model, but it's less artificial than the Ising model. I mean, the Jellium model was artificial too, because there's no such thing as uniform positive background. Here, at least we have a lattice, and how do you get from a real, a full understanding of, say somebody wants to understand iron and rewrite iron as a Hubbard model or something like a Hubbard model. Well, that's a whole art in itself, and many people have worked on that problem. You use some complicated density functional type calculation, and you reduce it down to local orbitals, and then when the dust settles, you get a model like this with some number for U. So getting the correct value of U is not easy, but for now, let's assume someone's done that hard work for us. So now we have this simple model on the lattice with only repulsion on the same site, and we want to understand its many-body physics. All of the physics I was discussing so far was really addressed in the context of some effective one-body effective theory. Okay, so what are we going to do? Well, this is the term that gives us the most difficulty because it's got 4 C's. So we're just going to apply our rule. We're just going to factorize it into all possible ways, just like in the usual trick for Hartree-Fock theory. So what we're going to say is that we're going to take n up and down. Oops. We're just going to replace it by Ni up, average value Ni down, plus Ni down, average value Ni up. Oh, I got that wrong. It's the same term. And then you get rid of double counting by adding this term here. Now you could also say, this is C dagger I up, C I up, C dagger I down, C I down. So by the rules of Hartree-Fock factorization, I should also worry about taking an expectation value of these two. So that is C dagger I up, C I down. So what is that? What about this thing? Shouldn't I be also giving that an expectation value? Someone want to comment on why I should or should not worry about this? Go on, somebody say something.
Does it vanish?
Yeah, well, it vanishes. Yes, you could say the following. Well, by spin somehow, this implies. Okay, so what would this imply? If this correlation function was non-zero, that means you have a matrix element between up and down. What that means, if you think about it, since the Pauli matrix sigma x points has a matrix element between up and down, if you think about it, that means that the spin points in the x direction. So we could well point in the x direction, but we are assuming, assuming the spin's pointing in the z direction. The ferromagnetic moment is in the z direction. So that's an assumption. So because we made that assumption for ferromagnetism in the z direction. Okay. So that's why it's zero. But that brings me to another point, which I didn't make. So if you look at this expression, it looks like it's not rotationally invariant. It looks like you've picked out the z direction as something special because it's expressed in terms of up and down. But an important point is that that term is actually rotationally invariant. It's the same in any direction. So it's a fun exercise to check, for example, that, suppose if I rotate my basis, so I can define my electron with spin in the x direction. Let me call it spin pointing this way. So let me drop the label I because it's the same label on everything. So we just drop the label I. So C with the spin pointing in the x direction is basically obviously 1 over root 2 C up plus C down. And the C pointing in the minus x direction is 1 over root 2 C up minus C down. So this is just the algebra of the Pauli matrices, and you can just see by changing bases and spins that this is true. So now the Hubbard term that I've written down is C dagger up, C dagger down, C down. And now I invite you to verify by using this equation that this is actually equal to C dagger right, C right, C dagger left, C left. And this relies on the fermion anti-commutation relation, and just you work through all of this and you find that this is true. And it's true not only for left and right, but any direction. You could put any other direction you wanted. I invite you to prove that in general, that this thing is actually completely rotationally invariant. So we made a choice in writing it this way to pick out the Z as special. And we're also making a further choice. And this first choice was just a choice of basis. It's not breaking any symmetry. But when we factorized it, at this point, where we picked out up and down, we made a choice that our ferromagnetic moment is in the x direction, in the up direction, up or down direction. It could have been in the left or right direction, but we just chose to call whichever direction the ferromagnetism moment points as Z. Notice that the Ising model here is not rotationally invariant. The Ising model has only one direction, which is presumably determined by some crystalline axis in the actual crystal. But the Hubbard model is fully rotationally invariant in spin space. And so we are making a choice which direction to put the magnetization. Okay, so we then what's going on here? We apply this rule, we apply this rule here to this term. and then plus the overall constant, which I haven't written down, plus constant, which I dropped. Then what do you get? Well, you get a Hamiltonian. This is a Hartree-Fock Hamiltonian now. There's the epsilon k term, which comes directly from this term. And then there's another term, which is C dagger k up, C k up. So that's coming from this term here. So this is an operator on a given site I. So C dagger I, Ci. And I'm assuming this is independent of I, this quantity, just like in the Ising model. And so sum on I, C dagger I, Ci is the same as sum on K, C dagger K, Ck. So that gives me just the number operator, sum over all K, with a constant, where this is U times N down, and this is U times N up. Okay. So what we have seen in this factorization, where we've chosen to polarize the spins in either the up or down direction, that the dispersion of the upspin electron and the downspin electrons are different. So the dispersion of the upspin electrons is Ek plus this constant. Dispersion of the downspin electron is Ek plus a different constant, because N up may not equal to N down. Okay, so what is the total energy of, so now I have these two unknowns, N up and N down, and I have to find the best value for them. And again, there's different ways of doing it, either by solving everything self-consistently or by minimizing the energy. So from now on, the logic is very simple, very similar to what the logic of the Ising model, except that the algebra is quite a bit messier. That's all. Okay, if I take my Hartree-Fock Hamiltonian, what is the total energy of this system? Well, you just add up the energy of all at zero temperature. You just add up the energy of the upspins and the downspin electrons, and you add up the energy of the states that are occupied. So if I'm working in some grand canonical ensemble, I'll occupy all the negative energy states. So this means that the sum over K is only over the negative energy of Ek. And similarly, the negative energies of Ek down here and Ek up here. And this overall constant is, of course, this constant here. Okay, excuse me. There's a sum over sites, but I guess I'll just drop that. Okay, so this is my Hartree-Fock energy, and it depends on N up and N down. So now I just change variables from N up and N down to the average and difference. So rho is the density, obviously. Well, okay, it's half the density. N up, so the density of upspins is rho on average. Well, sorry, the density of upspins is rho plus m over 2. The density of downspin is rho minus m over 2. So rho is the average density of up and down, and m is the difference of the densities. So m is what we call the ferromagnetic moment, which is n up minus n down in some units. So each electron has moment 1. All right, so we're not so interested in the overall rho. We're really interested in m, what the value of m is. So we can now plug this in here. And then what happens? Then we write it in the following way. So here we're going to use a trick which simplifies life a lot in condensed matter physics, which is we introduce something called the density of states. Okay, so then let me just quickly review that. So what is the density of states? So often, we'll meet things like sum on K, some function, need not be the Fermi function. Let me call it some function G, no, not G, because G is the density of states itself. Some function, some L of K. So this L is some function of, not of K, but of Ek, sorry, the energy at Ek. And what we do is we introduce the constant 1. So I have some dE, delta of E minus Ek, sum on K, L of Ek. So now I can just do this integral, that's just 1. So I haven't done anything. And now I reverse the order of integration and summation. So I'm going to pull out the dE and take the sum on K. Sorry. Okay. And what I'm going to do is bring this L out front, and I'm going to write L of E, not EK. And the reason I can get away with that is because this is only non-zero when E equals EK. So anywhere there's a contribution to this this expression here, E is equal to EK. So the only shady thing is I've interchanged the order of integration and summation. That's not too bad. It's part of the course for physicists. And this quantity here is what we call the density of states. So it's the number of states between energy E and E plus dE for the dispersion EK. So once you know, so once it's something we imagine we know for a crystal. And so the whole thing is just integral dE L of E G of E. Okay. So this density of states near the Fermi level or near the chemical potential is some constant. So typically in everything we're going to do in this course, we're going to just almost end up replacing G of E in the region it's important by G at the Fermi level, or that's at E equals 0, because the Fermi level in our grand canonical ensemble would be at 0 energy. Okay, so playing that trick, I can rewrite this expression here, exactly as this thing, where f of E is this function, E of theta of minus E. Okay. That just comes down. That's the L of E here, because I have E of theta of minus E right here. E of theta of minus E. But notice that the argument of plus spins has a plus UM over 2, and the argument has minus UM over 2. And then integral G of E, and then the n up and down becomes rho squared minus UM squared over 4. Okay. So I told you that, the algebra is a lot more complicated here, but in essence, we're doing exactly what we did for the Ising model. Just the functions are more complicated. These are some function of m, that's the energy. And at 0 temperature, I have to just minimize the energy. Okay. So there are these theta functions here, which are hard to deal with. So we kind of round them out. We take the theta function and write it as this is almost a step function, because it, well, I mean, right, okay. So yeah, as t goes to 0, you can see that it's equal to 1 for epsilon less than 0, and it's equal to 0 for epsilon greater than 0. So this is basically that function as t goes to 0. All right, so now I have some f of E, and for now I'm even thinking of that as a smooth function. And then eventually I'll send t to 0. In fact, this is exactly what you do. There's not a function I pulled out of a hat. It's exactly what you would do if I was computing the energy at finite temperature. You would just add, you would just replace this theta of minus E by the Fermi function. Okay. All right, so that smooth things out a little bit and easier to evaluate these integrals. Okay, so now assuming f is kind of a smooth function, you just expand it in powers of m. So you take derivatives of it and you expand it. And now you notice that the first derivative cancels between here and here because m comes in opposite sign. So you need the second derivative. So you get df squared dE squared times some m squared. And then you can verify that it's a nice property of this function that its integral is -1. I'll leave it for you to verify as t goes to 0. And so you plug everything and work it out. And so your Hartree-Fock energy as at 0 temperature is some constant minus the negative term, where you pick up the density of states at, right at the Fermi level, like I said you would, times the constant times m squared. That comes from expanding this to order m squared. And then you can go one higher, then there's a term here, which is m squared. And there are also terms of order m to the fourth, which we won't need. Okay, at least for now. All right, so now what you notice is that the Hartree-Fock energy as a power of m looks something like this. It's m squared u of 4 times 1 minus u g of 0. Okay, so from this you get what's called the Stoner criterion for ferromagnetism. And really the Stoner criterion has to do with this term changing sign. So to explain why that's the case, let's just go back to the Ising model. So for the Ising model, I had these two curves. So here, if I looked at small m in this region, here f went as some positive number times m squared plus something at higher order. Whereas here, right at this point, f went as some negative number times m squared. So the critical point where you went from the paramagnetic to the ferromagnetic state was when the coefficient of m squared changed sign. But to get the full curve, you have to go to order m to the fourth. In fact, here we had the full expression that has terms to all orders. And in principle, we also have the full expression here. So if you feel like it, you could take some g of e and actually plot this for all m, which I haven't done. And what you'll verify that the same criterion holds, that when this thing changes sign is when you have an instability to ferromagnetism. So in exactly the same way as in the Ising model, you would then conclude, as long as u is large enough, in fact, how large? Well, as though u has to be larger than 1 over the density of states at the Fermi level. And then the system will want to form a ferromagnet. Okay. All right, I'm running out of time, so let me just quickly, the rest of the thing is some discussion at finite temperature, which I'll talk about next time. But let me just quickly give you a summary of where this, how we could have guessed this without doing almost any work. And this is the basic physics of what's going on. So here I plot the free electron gas, where I just fill up all the states up to the Fermi level, both spin up and down. And a very convenient way to plot this is to take spin up states on the positive k and spin down state for negative k. Of course, they're present for all k, but I just plot them in a way like this. So now what's going to happen to get a ferromagnet? I'm going to take some of the spin down electrons and turn them up to spin up electrons. Now to do that, I'm going to have to pay some energy, at least as far as kinetic energy goes. So when I take these electrons and I put them up here, I'm going to have to pay some kinetic energy cost because the kinetic energy of these electrons is going to increase. So let me just take a tiny window of delta E. I'm just going to take a few of them and try to turn them over. So if I take a window delta of E and I move this over here, how much energy do I have to pay? Well, each electron is moving up by delta E. And how many electrons am I moving up? Well, so the energy cost for each electron is delta E. How many electrons? Well, there's the total number of electrons in this window G of E. What is the total number of electrons? Well, it's just the density of states times the window of energy. So that's the energy cost, G of 0 times delta E squared. But I'm going to gain some energy when I do this. And the reason I'm going to gain the energy is because I have this n up and down. If all, you see right here, if I write it in terms of the magnetization, you gain some energy when you have a magnetization. Because if all the electrons are up, the U term wouldn't operate at all. Okay, so if you just figure out how much energy you're going to gain, it's the total number of electrons in this window squared times minus U. So now you see that if U is large enough, gain of energy compensates the cost of kinetic energy, and you're designed to become ferromagnet. So this is just a hand-waving calculation, and here's a precise calculation with no cheating really, which gives you exactly this factor. Okay, I think I'll stop there. Any questions?
Yeah, I had a question about mean field. So I remember when we consider Bose-Hubbard model, we do mean field in kind of a different way, like starting from tight binding term and averaging this tight binding term. So can we do this in this model with fermions?
No, because you can't condense a fermion. So so in other words, for a Bose-Hubbard model, you take the kinetic term B dagger I, Bj, and you replace it by B dagger I, Bj.
Yeah.
Plus B dagger I. Yeah, this is what you're referring to. Well, the fact that this is non-zero relies on them being boson. That's the Bose condensate. But for electrons, this is, no matter what, this is always zero. You cannot have a non-zero expectation value because, well, electrons, you can't condense a macroscopic number of electrons in the same state.
Yeah, right.
So that's not a possibility here. You can get superconductivity, but you have to condense a pair of electrons, and that will be a couple of chapters. We'll be talking about that.
Yeah, thank you.
Sure. Any other questions?
So the mean field theory of Ising model predicts a phase transition in 1D?
Yes, it does. So it's incorrect in 1D. So as far as the mean field theory is concerned, you won't see anything special, any difference between 1D and 2D or 3D. And the only thing that depends on dimensionality here is Z. So Z would be 2 in 1D, it'll be 4 on the square lattice in 2D, and so on. So the value of TC will be 2J for the 1D Ising model in mean field theory. And that is incorrect. And the value of TC in the 2D Ising model is 4J. Well, that turns out to be an overestimate. It's not 4J, I forget what it is. It's, I don't know, 2 point something J if I remember. So it's off by a factor of 2 or something. In 1D, it's off by a factor of infinity, but that's special to 1D. So in 1D, it turns out the thermal fluctuations, the fluctuations of mean field are extremely strong. Not just near the critical point, but even at low temperatures. The reason, very simply, is that in 1D, you can get domain walls between up and down. And there's no cost to these domain walls just moving around freely, and that basically disorders the system at any non-zero temperature. I mean, that's what Ising solved the 1D Ising model exactly, and he found it didn't work and just gave up. I think he even left physics after that or something. He was part of his PhD thesis, from what I remember. Yeah, so it was only later that people realized in higher dimensions, actually, the Ising model does have a phase transition, and the Curie-Weiss mean field theory actually does apply, at least to some, as long as you're not too close to the critical point, and as long as you don't ask for the value of TC too accurately.
Okay, thanks.
I think I was also wondering, like, is this analysis of the Hubbard model also incorrect in 1D when we obtain ferromagnetism?
Yes, I believe it is. So I should say one thing. The Ising model in 1D is a ferromagnet at exactly 0 temperature. Okay, so now for the Hubbard model, exactly 0 temperature, yeah, I should be careful. It depends on the density. If you're not at half filling, if you're at some other density, I believe, someone correct me if I'm wrong. I don't know. Yeah, I mean, I don't think the Hubbard model has ferromagnetism at 0 temperature at any density. Yeah, okay. There's something called Nagaoka ferromagnetism, but that's some other limit. Yeah. But it can certainly have ferromagnetism in 2 dimensions at certain densities. I mean, we don't know for sure, but it's allowed.
Yeah, okay. Thank you.
But what is correct is that no matter what the model, Hubbard model, Ising model, whatever, if you go to non-zero temperature, then there's no ferromagnetism in 1D. That's always true.
Yeah, yeah. Right.
Okay, well, so again, no class on Friday. And I'm going to make the homework due on Monday. And there'll be sections tomorrow. But you're happy to discuss the homework, and we'll give a new homework set on Monday. Okay. So see you tonight for discussion if you care to come.